Solar flares and coronal mass ejections, CMEs, are captivating yet formidable phenomena originating from the Sun, the 4.6 billion-year-old star that fuels life on Earth. Solar flares are sudden, intense bursts of energy caused by the release of magnetic energy near sunspots. These events emit radiation across a spectrum, including X-rays and ultraviolet light, often reaching Earth in as little as 8 minutes. In contrast, CMEs involve the expulsion of massive clouds of plasma and magnetic fields from the Sun's corona. These ejections travel through space at incredible speeds, sometimes taking days to arrive at Earth, where they can interact with our planet's magnetosphere, causing geomagnetic disturbances. The historical impacts of solar activity reveal both the awe-inspiring and disruptive power of these phenomena. The Carrington event of 1859, the largest solar storm on record, caused global telegraph malfunctions and auroras visible as far south as the Caribbean. More recently, the 1989 Quebec blackout, caused by a geomagnetic storm, left millions without power for hours, while the 2003 Halloween storms disrupted satellites and GPS systems, demonstrating how vulnerable modern technology is to space weather. When solar activity interacts with Earth, the consequences can be profound. Geomagnetic storms induced by CMEs can overload power grids, causing blackouts and damage to infrastructure. Satellites are at risk of electronic malfunctions, which can disrupt communications, GPS, and internet services. Aviation is also affected, as flights over polar regions face increased radiation risks and potential communication failures. Even astronauts are exposed to heightened radiation levels during solar storms, posing serious health risks. On a more positive note, these interactions create stunning auroras, visible much farther from the poles during geomagnetic events, offering a beautiful reminder of the Sun's influence. Despite their unpredictable nature, advances in science and technology have improved our ability to monitor and prepare for solar activity. Organizations like NASA and the European Space Agency, ESA, rely on spacecraft such as the Solar Dynamics Observatory and SOHO to track solar flares and CMEs in real time. Early detection systems provide warnings that allow for protective measures, such as shutting down power grids, placing satellites in safe modes, or rerouting flights to avoid polar regions. Efforts to harden infrastructure against geomagnetic storms are also underway, ensuring that our technology is more resilient to these events. There are also intriguing aspects of solar activity that aren't widely known. Solar loops, for example, are massive arcs of glowing plasma that follow magnetic field lines in the Sun's atmosphere, extending tens of thousands of miles into space. These structures are both beautiful and scientifically significant. Researchers are also leveraging artificial intelligence to improve solar storm forecasting, offering the potential for more accurate predictions. The Sun's magnetic activity follows an 11-year cycle, with periods of heightened activity, known as solar maximum, increasing the frequency of flares and CMEs. While the idea of a killer solar flare is a popular trope in science fiction, it is not a realistic concern. The most severe solar events could disrupt technology and infrastructure, but they lack the energy to physically destroy Earth or wipe out humanity. Instead, the primary risks involve prolonged power outages, satellite damage, and economic disruption. Solar flares and CMEs are a testament to the Sun's power and complexity. While they can disrupt life on Earth, they also provide an opportunity to marvel at the forces that shape our solar system. Advances in technology and research have enhanced our understanding and preparedness, ensuring that we can mitigate their impacts and continue to thrive under the Sun's watchful gaze.